Okay, we have seen the Mendelian rules, and from this Mendelian rules, we can check how we can check the human populations. Because Mendel has done his experiments with the pea plant, and of course you can study with pea plants in very large amounts. They exist in various forms. You can have like thousands of them in a garden if you're a farmer. But when you come to the human, you cannot really do that. You cannot get thousands of F1 progeny in one single year in a single farm. Also, you shouldn't do that. This is why people do population genetics. And the population genetics, they apply the Mendelian rules to the human, and instead of making the controlled crosses like this, like he was crossing one plant with the other plant on purpose, what they do instead is that they check the population, they check the ratio of the alleles, and they check how they segregate, what kind of rules applied there. Okay, if they're okay in accord with Mendel or not. So what people do usually is that they check the gene pool and how the alleles segregate in these gene pools, and most of the time they follow the Mendelian rules. But rarely, well, not really, before first see how it obeys the Mendel, for example. You know, the albinism. Albinism is loss of the pigmentation. I'm sure you have seen some albino people. It's a recessive mutation. So it exerts its effect only and only when it is homozygous. So when people have children, one healthy, one albinism, people are going to be heterozygous. So if somehow these two people mate, their children can also be homozygous. So just by checking the families, just by checking the family history, you can reach this information, and you can do it by phylogeny, like this. So especially if you check the large phylogenies, you can learn how it is inherited. You can follow the inheritance pattern of a trait, like in this case albinism, because at first people didn't know how albinism was inherited, what was the responsible gene, etc. So they checked the genetic background. It followed. But when you have a large population, or when you cannot follow the families, you have to check the populations, and sometimes when you get the population genetics, things looks very strange, because the analogy of gene pool doesn't always work. Because in this gene pool, we assume that every time there is a new embryo forming, we are just going to randomly select two of the alleles for each gene. So first of all, they're not always random. Okay? In an ideal population, which is randomly mating, yes, this analogy works, and this gene pool is a good way to simulate the genetic movement, the interactions. But in real life, there are some problems that we encounter, and one of them is the cousin mating, consanguinity. Okay, in this consanguinity, when the cousins mate, like these two are cousins, it increases the chance of having a disease. So although this disease is recessive, just because there are many cousin marriages here, it violates the Mendelian rules. And when you check, it is half and half. And according to the Mendelian rules, there should be 3-to-1, 3 dominant, 1 recessive ratio in the population. But if you check here, it is 1-to-1. You don't see 3-to-1 ratio in the population anymore. So is the Mendelian wrong? No, but we don't see the Mendelian segregation because there was the inbreeding. Okay, cousin marriages or relative marriages, and hopefully not sisters and brothers. Okay, and we know that this inbreeding can alter the Mendelian distribution, that it can alter this gene pool, And altering this random marriages or random mating can create lots of problem. One of them is the Untitled syndrome. This is relatively recent. These people, by the way, this is not the first time these people are seen in Anatolia, because the cousin marriages are very common in especially some cities in Anatolia. They emerge time to time. So some travelers also describe them. These people, they, you know, there should be the brain here, and they are missing part of their brain, including the region which keeps their balance. This is why they are walking on their four, because on two legs they cannot keep their balance. They also miss the language center, so they cannot talk a proper language. Like the dogs can understand the words, they can understand the words, but they cannot put them in a context, and they cannot make them in sentences. So this is not a real language. This is not what we mean by language. So this is an example. Another example is the Habsburg family. So in Middle Europe, where the political power comes from the royal marriages, this family was really good at diplomacy, and it kept the Europe under control, and it was a time of mostly peace, because they were marrying in the family, and they have this very prominent jaw. Okay, at first it just looks a little bit strange, but it doesn't look like an abnormality. But as they keep inbreeding, by the way, they were really proud of their prominent jaw and this lip structure and this elongated face. And it was seen as a kind of proof that one person belongs to the Habsburg family. So this deformity, like the Siamese cat having this cross eyes, this deformity was taken as something cool. And this is why at every level of inbreeding it got worse and worse at one point, because the jaw was so prominent, it was so out, people couldn't really chew their food. And of course, this was not the only mutation that is accumulated. Some members of the family, or many members of the family, start to have mental retardation. Of course, if you want to rule Europe through politics, you should not have mental retardation. So this was the end of the family. So as you see here, this inbreeding brings the recessive alleles together. The recessive alleles, which normally are hidden when there is no consanguinity, they emerge. And because they emerge, this alters the population genetics. This alters the calculation that we do by Mendelian genetics. Okay, so we have some calculations on the basis of Mendelian genetics, but these calculations are altered when there is loss of consanguinity in the population. This is one of the examples. Another things that alter the Mendelian rules is linked genes. Now, let's remember the second law of Mendel, where we said that the alleles located on different chromosomes, like the C gene here and the A gene here, they're going to be totally independent. We are going to see any kind of combinations, like A1, C4, A2, C4, A1, C5, A2, C5. I mean, they don't depend on each other. They are totally independent of each other, because they can localize this way or localize this way. Because of this, according to the Mendel's second rule, they are going to segregate independently. What if you have another allele here, very close to C, D? No, it was not D. Let's say it is G, G2, and G8. Now, this G2 and G8, they are too close to each other. So first of all, they are on the same chromosome. So aligning the chromosome this way or this way doesn't change how C and G alleles will be segregated. This is the C genes and this is the G gene. So how they align at the metaphase plate, it doesn't change the segregation because they're on the same chromosome. They are going to be segregated together unless they are separated by a crossing over event. Now, check these alleles, B and A1. Let's make it smaller. So A and B, they are localized on two different parts of the chromosome, on two different arms of the chromosome. So most possibly they are going to be separated by a crossing over. Most possibly they are going to experience a crossing over event between them. So they are also going to segregate independently, A and B. But will there be a crossing over between C and G? We don't know. And if they are really close located, a recombination between them is quite unlikely. So in this case, we say that these genes are linked. Now, check this chromosome. A and B, for example, they are really close. So a crossing over event here is very unlikely. This is why we say that A gene and B gene is linked. This is why capital A is always segregated with capital B, and small a is always segregated with small b. Let's go back to the gene pool analogy. In the gene pool analogy, we randomly select alleles here, and we randomly select alleles from A, we randomly select alleles from C. So what kind of alleles we select from A doesn't affect C, and what kind of alleles we select in C doesn't affect G. But in this case, because they are localized on the same chromosome, they affect each other. Of course, if they are really far from each other, like A and F, they are going to assort independently because most possibly they're going to have a crossing over between them, because in every meiosis, in every chromosome, there are like 2-3 crossing over. So A and F, they are going to segregate independently. So they are going to follow the second law of Mendel. Check. But these two, they are going to violate the second law of Mendel. This is also why our calculations in population genetics sometimes can be wrong, because we neglect that the alleles can be linked, especially if you don't know where they are localized in the chromosome, like at the beginning of the 20th century when Thomas Hunt Morgan was doing it. He didn't know where they are localized, so it depended on it. Now, let's think about another thing. What is the chance of A and C being separated? Do you think it's going to follow Mendelian's second law, segregate independently or not? Now it depends. Sometimes they are going to assort independently, sometimes dependently. So just by measuring the crossing over ratio between A and C, you can also check the physical distance. So this crossing over ratio, the crossing over rate between them, is equal to their physical distance. The closer they are, less crossing over they will have. The further away they are, more crossing over they will have. And it is called 1%, 1 centimorgan. 1 centimorgan means 1% possibility of being segregated by crossing over. I could say that they are like 20 centimorgan away from each other. So they have 20% difference, or 20% chance of following the second law of Mendel. Okay.